Hello guys, so we're continuing the discussion of continuity. Sorry, I had to fix that. So part 2 of continuity. Today we're going to be looking at rational functions, not piecewise functions. So a rational function is basically a fractional function. There's going to be a numerator and a denominator, and those will be algebraic expressions. We are going to be doing a lot of factoring today. That's an important thing. The two types of discontinuity we're going to look at are called point and infinite. In this context, point discontinuity is sometimes referred to as removable, whereas infinite is referred to as non-removable. And I think you'll see why they have these other names once we get into it. Removal discontinuity has to do with canceling, like, it's a fraction, so you can reduce a fraction, or it's called canceling. And the graph will not have an asymptote. Non-removable doesn't cancel, and the graph will have an asymptote. So you hear me saying graph. Obviously we're going to be using Desmos, so let me pull this up, split the screen, and we'll get right to it. I'll be teaching more as I go, not a whole lot of notes going on. So what do the instructions say? Determine if each function is continuous at the given x value. If not continuous, classify the discontinuity. So we need to type this in. Y equals negative 2 x squared minus 16x minus 29. And at the point negative 4, doggone it. Wow, right there, negative 4. Clearly it's continuous. There is no gap, no hole, no break, no nothing. This is continuous. And here's a little tip. Every polynomial function is always continuous. Okay. Oh, should I check it? Should I check it? Do you doubt me? Number 2, continuous at negative 4. Okay, we could have been specific. I just wrote continuous, whatever. Okay, now an actual rational function. And we need to check the continuity at 2 separate points. So let's first look at the graph. Y equals, I'm going to hit the divide button first, and on top x minus 7, and on bottom x squared minus 7x plus 10. So we have this graph. It's a rational function, and did I type that in right? No, clearly I didn't. That's at 10. There we go. And look at that. So we have 2 asymptotes. Where is one of the asymptotes at? Does it appear to be at 2? Yeah, at 2. And the second asymptote appears to be at 5. What happens to the graphs, the pieces of the graphs at 2 at 5? This one shoots way down, doggone it, and it goes down. How far down does it go? Would you maybe say negative infinity? And the other side shoots way up to positive infinity, and the same for the other asymptote. One goes to positive and the other goes to negative infinity. So both of these discontinuities would be considered infinite. Oops. Because the graphs have asymptotes, they go to infinity. Infinite I'm going to abbreviate, at x equals 2 and x equals 5. Now I talked about factoring, so I'm going to go ahead and factor this denominator, x, 2, 5, minus, minus. Do either of these terms cancel with that term? No. In order to cancel, one of them would have to be x minus 7. So, because nothing cancels, that's why these are infinite discontinuities. If we check number 4, where am I? There we go. Infinite discontinuities at x equals 2 and x equals 5. Let's look at number 6. Y equals fraction bar x plus 2 on top, on bottom x squared. Now you see an asymptote there, but I'm not done typing it in. Minus 4. All right. I see an asymptote, and it appears to happen at 2. What happens at negative 2? Ooh, did you see that? There's a hole in the graph at negative 2. A hole in the graph. Remember from yesterday what a hole in the graph means? That means it's a point discontinuity. So our answer is, oh, doggone it, infinite discontinuity at x equals 2. That's where the asymptote is. And point discontinuity at x equals negative 2. Let me check the answer here. Number 6. Point discontinuity at negative 2, infinite discontinuity at positive 2. So it's worded the other way around, but it's the same answer. Now, what does this have to do with factoring? Well, let me factor this denominator. X squared minus 4 is a difference of squares. It factors into x plus 2x minus 2. And if so that's factored. It's not there anymore. We have x plus 2 on top, x plus 2 on bottom. Those would cancel out. And this fraction simplifies to f of x equals 1 over x minus 2. The one that's left behind, if you set that equal to 0, that one is your infinite discontinuity. The one that cancels, x plus 2, if you were to set that equal to 0, that one is your point discontinuity. And that's why that's called a removable, because when you cancel this out, it's like you're removing that factor from the equation. It's still a discontinuity even though it's removed, but it's like taking that single point out of the graph. You're creating a hole in the graph. So that is point discontinuity. So a little tricky there. Let's look at number 8. This one I'm going to go ahead and factor first. X plus 5 over x, 4 times 1 is 4, plus 4 minus 1 is 3. So if we were to set this equal to 0, negative 4. If we were to set this equal to 0, positive 1. Does anything cancel here? No, it doesn't. So what we should have are infinite discontinuities at both x equals negative 4 and x equals 1. Let's go ahead and graph it and see if that is right. Y equals fraction bar x plus 5 on top, x squared plus 3x minus 4. Oops, there's a 3 there on bottom. And let's look at this. I'll hit the home button. We have two asymptotes. Is one asymptote at negative 4? Check. Is the other asymptote at positive 1? Check. What do asymptotes mean? It means that that graph shoots up to positive infinity, goes up really high to positive infinity, or down really low to negative infinity. And that's why they're called infinite discontinuities. Let me check number 8. And there it is. Infinite discontinuities at both. Okay, now here, they're not telling us what numbers to look at. There's no at. So we just got to figure this one out on our own. Determine if the function is continuous. If it's not continuous, find the x-axis location, so the x value of the discontinuity. So 2 ways to do this. One, of course, is factoring. So I factor this denominator, x and x. 3 times 1 is 3. Positive 3 minus 1 is 2. If I set these equal to 0, I get x equals negative 3. Set the other one equal to 0. By the way, I just kind of glossed over it, but what's so special about setting the denominator equal to 0? Remember, in fractions, you cannot divide by 0. That's called undefined. So that's what creates discontinuities or problems with the graph. Denominators equal to 0 are undefined. So anyway, we should have two discontinuities. We have one discontinuity at negative 3, another discontinuity at positive 1. But since these would cancel out, this one's going to be removable, or a point discontinuity, whereas this one's going to be an asymptote, or an infinite discontinuity. Let me go ahead and graph this and show you. Now, what am I asking you to do? To do the factoring, or to do the graphing, or to do both? Ideally, you would learn well if you could do both. if either method gets you the right answer consistently, you can stick with that method, whether it's graphing or factoring. I'm sorry, I'm talking while I'm typing and I'm getting distracted. So, at -3, do we have an asymptote? Yeah, looks like it. If I zoom in, clearly -3. At +1, is there a hole in the graph? Right there it is. So you can use the graph to get the answer, or you can use factoring, or you can do both to verify your answer. So let's check. Number 10. Point discontinuity at 1, infinite at -3. And I didn't really write it out very eloquently, but there it is. Let's look at number 12. First I'll factor it. Well, really you can only factor out a 4. So when you set anything equal to 0, you can't set 4 equal to 0. It's a constant. You can only set a variable equal to 0, or a variable term. So x minus 4 equals 0. Add 4 to both sides. Doggone it. You get x equals 4. So clearly that is a problem that'll be undefined. Does this cancel with anything up there? No, you need an x minus 4 to cancel with another x minus 4. So we should have an infinite discontinuity at x equals 4. That's what I expect to see when I graph this. Y equals negative fraction bar, x squared on top, 4x minus 16 on, 16 on bottom. Is there an infinite discontinuity at 4? Well, clearly there's an asymptote there, and yes, it does happen at 4. There's 5, so one place to the left. That looks like it is correct. Did it with algebra? No. Did it with algebra? Did it with the graph? Let's check. Infinite discontinuity at x equals 4. Correct. Number 14. Again, we'll do it with factoring, algebra, and we'll do it with graphing. So the numerator, x 5 times 4 is 20, minus 5 minus 4 is -9. The bottom is x minus 5. So what makes a discontinuity is whatever makes the bottom equal 0. You don't set the top equal to 0, just set the bottom equal to 0. X equals 5 will be discontinuity. Will it be infinite or will it be a point? So the question is, does this cancel with anything? Yes, it does. That makes it removable, or a point discontinuity. This is a point discontinuity at x equals 5. You might say, well, what about x minus 4? That's in the numerator. That doesn't matter. All that makes discontinuities in rational functions is the denominator. Let's go ahead and graph this and see if I did everything correctly. Y equals negative x squared minus 9x plus 20 on top, and x minus 5 on bottom. And do I have a point discontinuity right there? Absolutely do. That verifies my answer. Number 14 should be correct. Point discontinuity at x equals 5. Okay, the last one is number 16. Well, look at that. It's a polynomial. What did I just say when we started? All polynomials are always continuous. I'm going to go ahead and graph this just to prove it. Oops. Type it in correctly. And yeah, now there is no points anywhere that there's a gap, no asymptotes. This keeps on going forever and ever and ever. If you were to draw this, you would not pick up your pencil. You would just die of old age because you keep drawing to infinity. So this one is simply continuous. And if you check 16, it says continuous. Okay, so there's discontinuity when it comes to rational functions, the two types, point and infinite. You don't have to use the words removable and non-removable. They are terminology that matters, but it really comes into play when you're factoring and the idea of canceling. You're sort of removing a term. So the point discontinuity is referred to as removable. Infinite creates an asymptote, non-removable. Okay, try these odd problems, graph them. Like I said yesterday, it might be tempting just to copy the answers up here because I'm never going to know the difference. I'm just going to ask you, well, I guess I'm going to see some work when you do the factoring on various problems, but do the honest work, graph it on Desmos. Contact me if you have any questions. Other than that, good luck, and I will talk to you later.